Hello everyone, welcome to my YouTube channel. Today I am going to talk about the HEC-RAS 2D modeling. There are two kinds of modeling in the HEC-RAS we can simulate. They are 1D modeling and 2D modeling. 1D modeling basically simulates for the river scenario which have the fixed flow path, and 2D modeling simulates for the rivers which have both directional flow, longitudinal flow and latitudinal flow. It can simulate the floodplain also, floodplain scenario in the both directions, but in the 1D modeling it simulates only for the longitudinal flow. So let's talk about the essential data for the 2D modeling. Before that we have to create a folder name as like this, and assign the different kinds of folder for the essential data. So I had already created a folder named as the HEC-RAS 2D trial. Inside this folder I have 5 different folders, one for DEM, another for flow data, and it depends on the which type of flow data you are going to use. Today I am going to use for the peak flow return period data. I am going to use 100-year return period flow data, and another is for the land use land cover, which will be used for the Manning's roughness coefficient, and this one is for the projection file, and which will be used in the HEC-RAS as a projection file, PRJ file, and another is for other relevant shape file which can help in the more visualization. Let's open the HEC-RAS software. First of all, you have to create a new project. I am going to assign a folder, and I am going to create in the I'm going to create in another folder. Here is the modeling related M-techent project, and let's create a HEC-RAS 2D model, and let's create a name for this file, for this project. I'm going to create like demo 1, okay, demo 111, okay, demo 11. It will be file title for this project, and okay, and click on OK. Also you have to note that which unit system you are going to use. First of all, you have to assign. It is already by default it will be in the US customary, so I am going to use metric system, so SI system, and click on S, and then after you have to open RAS mapper. First of all, you create projection. You have to set the projection. You have to set here, and I had already put in this folder as .prj file. You have to import that projection file. Here is the projection file, HEC-RAS 2D, and here is the projection file. Okay, let's open it. After this you have to apply and click on OK. Now it is in the projection file. This projection file is for the 44 projection, 45 N projection, because I am going to use in the western part of the Nepal, which lies in the 45 N. If I am going to use in the eastern area of Nepal, then it will be 44 N. So I am going to use this type of projection file. This projection file is of the UTM zone, so it is in the 45 N projection file. After setting up this projection file, you have to go to features, geometry, and just right click on this, add new geometry. You have to give a name. As for now I am going to take this as demo 1. Okay, now you have to click on edit geometry. This one is the edit geometry, or also you can just right click and click on this. After that these rivers cross sections, these are for the 1D modeling. So for 2D modeling you have to first of all create perimeter. So search for the perimeter. Here in the 2D flow areas you have to click on this perimeter. Before this, first of all you have to input the DEM files, because we are going to work on that DEM file. So we have to import the DEM file. For this just click on the terrain and right click, create a new RAS terrain and click on this plus, open that folder, and here it is DEM. The DEM file should also be in the same projection file. Here it was already in the 45N. So now just click on create. Okay, and then after you have to click on the before this you have to import some features, because I am right now confused where I am going to actually work on. So add existing layer, and here open the folder, and here it is shape files. The targeted river is as Solu river, because I am going to use the western part of the Nepal in the location of Solu catchment. The Solu river is going to be modeled. So import this polyline river shape file. Just you have to change the color of this. Right now I am going to create it in blue color. Okay, now it is seen. Although the catchment area has a bigger size, but for now we are going to select a little section. So also you can import another catchment area boundary. The catchment area for this Solu river is this area, because it is bigger in size. So for now, to learn about this modeling, just I am going to use certain area. I am not going to use whole this catchment area. After importing these files, I will create a perimeter. First of all, you have to create a perimeter area in which you are going to model the 2D modeling. So by seeing the river area and by estimating the floodplain of this river, you have to assign the perimeter. You have to enclose with the polygon. I'm guessing this much area will be its floodplain. When the flood scenario, the flood extended area will be in these areas. So I'm going to enclose with this perimeter. This much will only this much area will be modeled in this HEC-RAS. So first of all, you have to draw polygon area using this perimeter tool. Before this, you have to be clear whether where you are going to assign the inlet area and outlet area of this river. For now, I am going to keep the inlet region in this section and outlet in this section. So I am going to create the perimeter as in this area. Let's take this as perimeter 1. Okay, and you have to give the grid size of this perimeter, because there will be creation of the grid size in this perimeter boundary. So by default it is already in 100 100 by 100 size. So I am going to use as 50 by 50 and generate. Here you can see the mesh are created. Also here by default the Manning's value n value is 0.06. let's keep it as it is and close this. You can see by zooming in, here you can see small boxes. These are the mesh size. It is of 50 by 50 size, because we already assigned as 50 by 50 for each cell size. So the model will perform every flow scenario in this each pixel size. So if you give a small size, then there will be more boxes, more mesh sizes, and then the model will also be more finer. For now, for the just learning, I have created the 50 by 50 sizes. Now after this creating, you have to give boundary conditions. Boundary conditions are for the inlet and outlet, where you are going to give the inlet of this river and outlet of this river. So for the inlet and you have to see for the boundary condition lines, here it is, and just draw the line outer of this polygon boundary. You should not draw the line over the polygon, there will be error. So you have to create just near to the polygon. Let's say the inlet comes like this. Let's rename it as inlet. Okay, inlet, and also give for the outlet region. For outlet region, you just give like this. Okay, now rename this as outlet. Just click on OK. Let's off this river file, and this one is the perimeter. One thing I want to show you that you have to, after creating all these polygons, you have to generate computation points. And then after you have to edit to the here, and let's check whether it is in the 50 meter or not. And then after you have to force. Okay, and here is another also feature as refinement regions. This refinement region is also same as the perimeter, creating polygons. It is used for the more refinement. We firstly created this wall perimeter. This will be the main region for the river, for the study area. Then if you are going for these refinement regions, it will be used only for the more refinement. For example, if you want to give the more resolution, higher resolution on this main flow path only, then you have to create this, you have to use these refinement regions, and for that section only, for that section area only, you can give another high resolution, let's say 10 by 10 meter in these refinement regions. For example, I will use this for more information. and here it is refinement regions. For example, I am going to use this for only as example. Let's say I have finalized this perimeter boundary and I am adding another refinement regions. This is the river flow path, so I am going to use this refinement regions in this section. Create like this. Refinement region 1, okay, and let's say this edit it as the cell size as 20 by 20, okay, and then you have to enforce all regions. Okay, here you can compare. This one is the perimeter, this one is of the perimeter, and this is for the refinement regions. Let's compare the cell size. Here it is in bigger size and it is in small size. It is clearly seen that this perimeter is more higher resolution, is of higher resolution, and this is of lower resolution. So when the HEC-RAS models the river after flowing of the river from this upstream to downstream, this area will be of more accuracy. For now I am not going to use this refined area because it will take more simulating time. Okay, now let's save it. Also do once again let's generate computation points. Okay, okay, let's save it. Here the computation points is off. If you want to see the points of computations in each cell, you can just click on this and you can see the points of computations. After this, save this file and close this one and open the geometric data. Also you can see from this also geometric data and file, open geometry data, just click this and okay, here it is. Now save this geometry data, okay, and go for the flow data. So in the edit section there is on steady flow data. We are going to use on steady data. 2D modeling always use on steady data. It cannot simulate for the steady analysis. So we are going to use on steady flow data. Here it is already seen that inlet and outlet, that we already named this file. Here it is in this section, perimeter 1 of this inlet and outlet. Just click on this. For the inlet we are going to use flow hydrograph. Before this we have to see for the flow hydrograph. Here is the flow data. Just open. I had already created a dummy data. This is for the only practice purpose. This is not a real data. I had created for the 100-year return period. It was of 100-year return period, had this flow data 424.746 cubic meter per second, and using a mathematical modeling I created this flow hydrograph. We have different types of options, different types of tools or mathematical techniques or any other equations which can create the flood scenario flow hydrograph using the peak discharge. I had used the unit hydrograph method to simulate for the flow hydrograph of this river. Let's see the graph. Here it is like this. First of all, the plot scenario goes to the peak, and it will be in the normal as in the as of the river base flow. Okay, let's copy this flood flow. Also, you have to note that of what ordinates you are going to use. So I had already assigned this as the 100 ordinates. It is simply a number. How many number you are going to use the data. In this scenario, I am going to use for the 100 ordinates. So in the flow hydrograph scenario also, you have to give for the 100 ordinates. Now copy this and just paste it here. You can give a date. So I am going to use this flood scenario as, let's say the flood peak flood scenario is of 2024 September 10. Okay, September 10. Okay, now it starts with the time from, let's say 12:00. Okay, now it started with the 10 September 2024 midnight time, and the flow scenario can be seen from this time to the last date is 14 September 2024 in 15:00 time. That means 3 p.m. and you have to note this initial time and final time also. So it will be easy in the further input. Because we have to input this time, date and time in the simulation, during simulation running time. So I am going to note it out. 10 September. Okay, let's write it here. 10 September 2024 12:00, and the ending time is 14 September 15:00. September 15:00. Okay, and another thing you have to note here is easy slope, the energy gradient slope. Let's say it is 0.007, and click on plot data, and you can see the flow hydrograph, and save this data. It is already saved. Now you have to click on the OK and save this flow data as let's say demo flow. Okay, and for the outlet, if you have the stage hydrograph obtained from the Department of Hydrology and Meteorology or other sources, you can use the stage hydrograph, or you can use the gauge station data. For now, due to data unavailability, I am going to keep this outlet as normal depth. Let's say the normal depth to be as 0.001, and let's save it. Okay, and go for the run, and this run you have to see for the unsteady flow analysis. Before going for other section, you have to see for the option and computation options and tolerances. Here you have to check whether the gravity value is exactly in the SI unit or not. Here it is in 9.8, it means it is in metric system, it is correct, and click on OK. and then you have to click geometry processor, and this we don't have sediment data, so let's leave it as it is. And here you have to note that copied time date. Here it was 10 September 2024 starting date, and 1200 and ending date was 14 September 2024 and it is 1500. Let's simulate for the 1 minute or 5 minute let's simulate for the 1 minute. Okay, 1 minute. Computational in time interval, let's take it as 1 minute, and click on the, and possibly you have to save this plan, save plan as demo plan, and the shortcut key also as demo plan, and click on compute. After few minutes it will be complete. I had used the computational interval as high value for more accuracy, and for more realistic scenario you have to use finer smaller computational interval, and you have to use higher resolution of the grid size. I had already used 50 by 50, which is quite higher. If you use 20 or 30 meter, then it will be more finer and more accurate. After a few minutes, it is now in the final simulation period. It is finished. Let's see here the simulation run time. It took as 2 minutes 57 seconds. Let's close this and also close this. Let's see for the result section. Demo, close this, and here you can see the DP as I took as the plan. You can see the max and update laser with the view for the flow scenario. Let's see like this. Here you can see the maximum value is in the maximum depth value is in the dark blue, and this light blue color is low depth value. For this reason 49.5 meter is the highest depth. It seems like too much higher value of the depth, because we used the demo data. It was not more real data. So for this video is only for the HEC-RAS tutorial, only for this how to run the simulation. You can use the real data and practice more and more for the more realistic scenario. And if you have to see for the velocity here in this section, the dark blue color is the lower velocity, and this dark red color is the higher velocity. If you have to see for the overall area, then you can see the higher values of the velocity, because this upper region of the catchment of this river shows the higher velocity because of this steepness of the topography, and this must be the floodplain area. This must be the flat area, so it has lower velocity. other different features also you can see from this HEC-RAS just by clicking on this edit map parameters, result map parameters. Here you can see other inundation boundary, fraud, current, and shear stress, and other different. You can just click on this and go to save map. For the stress analysis of the floodplain area, you can see here it is as it looks like this. In this region the shear stress has lower value and other have the higher value.